Let's talk about the behavior of time series models with this time roots on the unit circle, that is, roots of the characteristic equation of 1. And specifically, we'll be looking at those factors that have a root of 1 that indicate wandering behavior. What are the behaviors associated with these type of time series models? So to be specific, actually, we're going to start off with a stationary model that's super close to a non-stationary model. Notice an AR1 here with a phi1 of 0.99. So just getting our head wrapped around where we are, we're going to load TSWGE. I'm going to get my phi1 of 0.99. Again, looking at the factor table, we see that here the root is barely outside the unit circle, and that it's associated with wandering behavior. And then there's the factor. But I'm going to go ahead and put in here so we can visualize it. 1.0101. And the imaginary part, it's a real root, so there is no imaginary part. We'll explicitly put in 0 there. And if we do that, we can see that it is just barely outside the unit circle, but still stationary. And so what does that mean? It means it'll be attracted back to an overall mean. It might take it a while to get back there. It may go on extended runs above and below the mean. But let's see exactly what we're talking about with that. Is we'll still have our variance of the AT being 1. We're just going to look at a small series here. Again, when you have extreme positive correlation, you can go on these runs above the mean or below the mean pretty easily, even in a stationary model, even though phi1 here is 0.99, or given that phi1 is 0.99. So we'll go ahead and run this. Let's go ahead and run that. And there is, if you use seed equals 2, you'll get the same exact one. And over 30, it looks like there's that's just the way it's gone. It looks like it could even be some sort of positive trend, some evidence of that. But the point here for us right now being that we know that the mean is 0, because the way we've generated this series is we don't have a mu term in here. Thus, that mu term is effectively 0. So we know the mean overall is 0, but the sample mean of these 30 is considerably above 0. So let's look at a little bit more information. Maybe we'll get a better estimate of mu, because x bar, the red line, x bar is not a great estimate. It's an overestimate of mu at the moment. So again, remembering that phi1 is 0.99, autocorrelation is thus 0.99. I will do that, and it still hasn't really moved that much. It's still above it. It looks like it's gone above, below, it's wandering, it's going down and up, and it's still gone up. But we know that its mu is 0, and it's still this overestimate. So I'll go ahead and see if 3,000 observations is enough to get a good estimate for x bar to be a better estimate of mu. And we do that, and it's gone up and down a whole bunch, right? It's clearly attracted, or there's a lot of evidence that it's attracted somewhere, but that red mean is still at 5. I think it's gone up since the last one was about 2.5. We know the true one is at 0. So x bar may not be a great estimate of mu in these unless you have a lot of observations, is kind of what we're seeing here. But at 30,000, what does that look like? And that is a much better estimate. And if I go up to 300,000, right, then we'll let that sit here for a while. That root is just outside the unit circle. We know it's attracted to some overall mean, and at 300,000, it's about 0. So we know theoretically what's going on. It's had plenty of times to go above, below, and they all average out. That's what will happen with a stationary model. If phi1, an AR1, if phi1 is closer to 0, then you'll be able to get a better estimate. X bar, the red line, will be a better estimate of mu much quicker. But that is something to play around with. But that's a stationary model. Let's now play around and see the contrast when we suddenly just inch this up just a little bit more on the phi1, and thus obtain a useful non-stationary model with wandering behavior, but this non-stationary wandering behavior. So we'll go ahead and make that 1. We'll confirm with the factor table that we do have a root of 1. The absolute reciprocal of 1 is, of course, 1, and that is associated with wandering behavior. And I'll go ahead in here and change that to 1 on the root. Imaginary part is 0, so we can confirm again visually that the root is directly on the unit circle. And what does that do? We'll take it back down here to 30. What does that do to our realizations? Well, not a lot right off the bat, right? This looks like a pretty similar series, but if we take it out a little further, what happens? So I'll let this be 300, and we'll take it out. And this time it looks like it's gone, but this time it's gone even above 5, only in 300. So what we'll find with non-stationary wandering behavior with roots on the unit circle is that it's not attracted to a mean, and it has infinite variance. So let's keep going. Let's see what happens at 30,000 because at 3,000 because it stayed at least stable, and we knew it eventually would get back to 0. But now it's just unbounded. This thing's just wandering. Didn't have to wander up, but it's wandering without bound. So easy now. The mean is now estimated to be like 75, whereas we know there isn't a mean for this one. But if it was stationary, it would come back to the mean of 0. So let's go ahead and do for 30,000, see what's going on. Right now it's up to 125, just because it looks like it's going up and down, but it's not attracted to a mean. And its variance, like if we give it enough, it'll eventually explore beyond 200 and beyond 0. Let's see how far we can get it to go in just right. Infinity is a long, long, long time, so this is not very. Theoretically, we're not any closer than at any other time, but now it's generating 300,000. Now it's had a chance to explore up to 600. It looks like it's on its way down. I'm going to do one more time. I'm just going to go up to 1 million and see what happens. We'll sit here and talk about it for a minute. It's 100,000. So let's go to 1 million. So this was 300,000. We're going to go 3 times that. Let's hope I didn't go to 10 million. Oh, I did go to 10 million. Oops. Well, we might be here for a while for this one. Maybe longer than we intend to go. 10 million will take a bit of time. But, actually, no, that was just 1 million. 1, 2, 3, 1, 2, 3, 4, 5, 6. It was just 1 million, but it has explored over 600, turned around and gone back under negative 200. If you keep doing this, it will keep exploring higher bounds and lower bounds. It has no mean, or sample mean now is up to about 300. It's not attracted to a mean, and it actually has infinite variance. So one last thing I wanted to show you here at the end was some TSWG functions that will kind of get at the same idea. So if I did gen.arma.wge, arma being a stationary model, let's say I just did 100, let's say I did phi equals 0.99 again, and let's say that I had mu this time equaled 30, let's say. So that's essentially just in here going to add a 30. And if I did that, and if I put in AB line H equals, actually I'd have to do this, so we'll do a little inline coding. So I say R for realization. I didn't specify a seed. I'll specify a seed here so that we can all do the same one. Let's say Sn equals 1. And so we do that. We remember it's got that increasing trend in the beginning. But then if I do AB line H equals mean of R, color equals red, then we'll drop our line on there. And we knew that we gave it a mean of 30, and it's pretty close to 30. But let's add a little bit more observations onto it. Again, this is the stationary model, and we'll do that. And we'll put AB line on there, and right, it's gone up a little bit, but because I've got 0.99, so now I've got to do a few more just to make it kind of settle our example down here. But with 0.99, that X bar is able to have a lot of variance. It's able to get away from U for smaller sample sizes. So I'll go ahead and do that, and then drop AB line down on there, and it's a lot closer to 30. And I encourage you to play around with that. Let that go even bigger, and it'll get steadily converged to 30. But what happens if I do the same idea, but instead of ARMA, I do ARIMA.WGE, and let's, instead of phi equal 0.99, we say D equals 1, where that's 1 minus B quantity to the D. And if it's 1 minus B, then that's 1 minus 1B, and that is a root on the unit circle. So this is a non-stationary model with roots on the unit circle. It's the same model I generated up here. So let's see what that does with, let's just say 10,000. Again, I've let mu equal 30, but it doesn't matter. We can kind of give it a starting point and put that in the equation, but it's not going to matter mathematically to the realization when it starts generating realizations. So if I do that, yep, right. So it's the mean of this is now negative, but it instead of 30. But that's the whole point, is it's not attracted to a mean. Even if you add one into the equation, once you have 1 minus 1b, it won't matter. So let me take that out a little bit further, right? Let's take that to 100,000. And we do that. And right now that's below negative 100. And there's no stopping that eventually. If you had the realizations go long enough for it to go up to 1,000, for that red line to go, there's just no telling where that line's going to be because it's not attracted to some kind of mean. So highly encourage, the best way to learn about this is to just play around with it. We have a great laboratory here and a great library with TSWGE to play around with this, to have little questions and answer them yourselves, and play with the sample size, play with the phi, stationary, non-stationary, just confirm the properties that we know exist.